So in general, we are all very familiar with friction in our everyday life. We know that if we have an object and this object is sliding over a surface, probably we want this object to go faster. So we want to reduce friction. And then there are other cases in which we have this object which is going way too fast. So we want to increase friction. So friction in general results in an energy loss, so in neat waste. And if we consider small devices where we have surfaces at the very small distance, which are sliding one over the other one, having a film of liquids between these surfaces can not only prevent the wear of the surfaces and so the mechanical failure, but it can also control and manipulate the performances of these devices. So in general, what we do, we add between these surfaces some lubricants. In order to be a lubricant, a good lubricant, we want that the performances, the friction response is basically constant independently on the external conditions such as temperature, or if you want, the load that we are applying. So for example, if we are applying a load between these surfaces, we want the lubricant, the film, to be constant. We don't want the surfaces to get in contact because the lubricant is squeezed out. Ionic liquids actually has all these properties and have been considered as good lubricants. They are molten salt, so we have anions and cations. And these are the kind of ionic liquid that I'm gonna use in that talk. So they're based on the imidazolium cation. So what's happened when we confine the ionic liquid? In general, if we consider charged plates and we confine the ionic liquid between two negatively charged surfaces, what we see is that they actually structure itself in different layers, which are cation-rich or anion-rich layers. And from experiments, what we know is that if we apply a load at these plates, we can actually see a change of the thickness of these confined films, and the change is happening as along these branches. So when we jump from one branch to the other one, what we see is that there is a decrease of the thickness and a decrease of the number of ionic liquid layers, which are basically squeezed out. In that case, 2 layers of ionic liquid are squeezed out in order to maintain the electroneutrality of the confined film. Always from experiment, we know also that if we apply a different potential of across these 2 surfaces, we can change the composition of the confined ionic liquid, and then we can also tune friction, the friction force. And this means that we can this introduce actually the idea of electrotunable friction. So the response of the lubricant is dependent on the electric field. From simulation, in our group, well, we studied that in our group since a while now, and what we know is that if we the friction force is actually changing with the surface charge that we are applying across on these plates, and this and independently on how accurate the model is. So here in that case we have a primitive coarse-grained model in which the ionic liquid is modeled as a sphere for the anion and a sphere for the cation. And also for a more accurate model for the ionic liquid, we see that the friction force is increasing with the surface charges and feature a maximum at a specific charge density. So In this talk, we want to understand how we can tune friction of a confined ionic liquid. And the first things that we are gonna do is we change the composition of the ionic liquid by changing the cation length, the chain length of the cation. And we can also tune friction by changing, as we saw before, the electrostatic potential. But what's happening if we change, for example, the polarity? So let's say we have one of the slab which is negative and the other one is positive, or if both are negative or if both are positively charged. So we are going to do that by using a non-equilibrium molecular dynamics simulation. And this is the system setup that I'm using. This reproduces experimental setups. So we have these two plates, these two walls, which are immersed in bulk ionic liquid. And so we have this confined region in which the ionic liquid, the anion can enter or go out freely. We charge these surfaces by charging each atom of the wall. Just to give you an idea, this is the charge for mica substrates. And then what we do, we apply the load by accelerating the atoms on the wall. And then we simulate the shearing by attaching one of the wall to a spring and pulling this wall. In this simulation setup, the thickness of the confined ionic liquid can change. Okay, so the ionic liquid was saying that we are investigating now are these imidazolium-based ionic liquid. And we model them by using a coarse grain model. In that coarse grain model, we have the head of the charge group of the cation, which is composed of 3 groups. And then we have a tail, and then the anion is modeled just as a sphere. Okay, so as soon as we confine this ionic liquid, we apply the load and we pull we apply the load and we pull one of the wall. What we observe is that the ionic liquid structure itself in different layers. So we have the cation layer, the anion, and so on. And then the thickness is actually changing for the same load with the chain length that we are using. And if we see the pressure versus distance versus thickness curve, we see that we see these branches, we see the jump between one and the other one, which corresponds to the squeeze out of the 2 layers of ionic liquid. And also what we can learn from this is that for smaller ions are actually less compressible. So we have larger thickness, bigger thickness for small ions than for longer chain length. And also the pressure that we need in order to squeeze out these 2 layers is actually bigger for small ions than for long cations. The friction force is, we notice that is actually increasing with the chain length. And this is happening for all the pressure analyzed. However, the increase is smaller for a larger pressure. So in general, small ions are better lubricants because they are less compressible, so they change less with the load, and also the friction force is actually smaller. Okay, now what's happening if we change the surface charge applied on the plates? So we see also for this more accurate model the maximum in the friction force as a function of the surface charge. In that case, what's happening is that we are reorientating the cation. So if we consider the spheres, these red spheres is the polar head of the cation, the yellow part instead is the tail. If we see the snapshots and this top view of the first layer next to the wall, we see that for low charge density, the ionic liquid is basically lying flat on the surface. And as soon as we increase the charge, we see that it actually orientates. And here for the highest charge, we see next to the wall, just the heads of the ionic of the cation, and then the tail are mainly facing the inner part of the confined ionic liquid. This is something which was observed already in experiments. So in these experiments, for example, they were increasing the electrostatic potential, and they were seeing exactly this. So the reorientation of the cation, and then which was then for higher potential lying perpendicular to the wall. From this plot, we saw also that this maximum is connected, is also dependent on the pressure. So for low pressure, we don't see this maximum. We can understand something by, we can understand the behavior by checking the velocity profile of the confined ionic liquid. So the wall is moving at 5 meters per second, and we see that for 10 megapascal, where we don't see the maximum, the velocity profile of the ionic liquid doesn't change mass significantly with the surface charge. Instead, for a larger pressure, we see that at low charge density, the ionic liquid is moving basically as a full a solid block, so at the same velocity, which is half of the one of the wall. And then the shearing, the slippage plane is happening actually between the ionic liquid and the wall. And then as soon as we increase the surface charge, the cation is orientated, and the heads are basically stuck on the wall, and they are moving at the same speed of the wall. And the shearing is happening between the different layer of the ionic liquid. So this maximum is actually connected to that change, that shift of the slippage plane from this interface, the ionic liquid and the wall, and the different layers, the different layers of the ionic liquid. Okay, we then try to change the polarity. We use, we compare the negatively charged surfaces with the results for negative and positive walls with positive and positive. What's happening here? Well, when we change the polarity, we are changing the structure of the ionic liquid in the confined region. We are changing the thickness, we are changing the number of layers that we, that we have. What we observe is that the friction force is lower for the case in which the two surface charges are positive. In that case, we have more layers of anion, and the anion layer is actually close to the wall. So this means that the anion layers provide a better lubrication, if you want. Okay, now we move one step further. So we analyzed a more defined corn-screen model, but we want to see what's happening if we use an atomistic model. So if you want, we describe the ionic liquid with a more accurate force field. Again, the simulation setup is exactly the same. So we have these two walls, they are charged, we apply the load on the walls, and then we pull one of the slab. In that case, again, what we observe is that the ionic liquid is creating this alternating layer of positive and negative charge. The layers, the number of layers are actually dependent on the load that we are applying and on the chain length of the cation. And in particular, we see also in that case that for the same load, the smaller cation is actually less compressible than the larger cation. The friction force also in that case is increasing with the chain length, and it depends on pressure as well. We checked the friction force as a function of the surface charge. In this case, as for the coarse grain, we observe a reorientation of the ionic liquid inside the confined region and the shift of the slippage plane from the ionic liquid the ionic liquid wall interface to the inner part of the region. If we compare this data with the the results we had for a coarse-grained model, we see that the friction force, the maximum is appearing at the same surface charge density, but the friction force is actually larger. This can be connected to several factors. Well, the structure is different. The number of ionic of layers are different, but also the transport properties of the two models are different. In particular, if you check the diffusion coefficient for this atomistic force field, is actually 1 order of magnitude lower than the experimental value and then the coarse grain one. From this, however, we can from the atomistic model, we can get more information about the structure itself of the confined film, but the physics, we can get it also with a very primitive model. So to conclude, we saw that the structure of the confined ionic liquid can change the structural forces and the friction force. And we saw in particular what's the influence of changing the chain length of the cation. We saw that in that case, the same load, the short cation basically are better lubricant because they are less compressible and the friction force is lower. We saw also that the friction force change with the charge density, but also with the pressure. And we saw that with the charge density, we can see a maximum in the friction force, which is connected to the reorientation of the anion, of the cation, and also to the shift of the slippage plane from the solid liquid interface to the inner part, to the inner layers of the confined region. And then finally, we saw that changing the polarity of the electrodes can also tune friction. And in particular, we saw that that anions are better lubricant than the cation for this ionic liquid family. So with that, I would like to thank well, the group and all of you for listening. Yeah.
Thank you, Silvia. That was great. So we have a few questions. Johannes,
Yes.
If you'd like to unmute and ask your question.
Yes, I'll start. I'll share again if you don't mind. Sorry, I stopped, but it could be easy to share it.
So
yep.
My question was, so in your simulations, you always have sort of a fixed chain length, right? And I was just wondering, in a real ionic liquid, do you have actually a mixture of chain lengths? And
yeah,
if not, yeah, go ahead.
Yes, well, in most of the experiments, they can reach actually very good purity. Also, like they can remove, for example, water very well. In this particular study, I haven't studied a mixture of ionic liquid, but there are already work also from Fernando with mixtures of different ionic liquids.
Okay, thanks.
Alex, do you have a question for Silvia?
Yep.
Yeah, I was asking whether you checked shear velocity dependence, and this shear velocity 5 meters per second, as far as I understand,
yes,
what you say, is quite high. So
yes, it's quite
much higher than any experimental.
So we checked actually different velocity. Of course, like the friction force depends also on the velocity. In that case, well, with that velocity, we actually still see the stick-slip motion that we see observed in experiments. I can probably show it here. Can you see it? So here we have the friction force as a function of time. And with that velocity, you are still seeing the classical stick-slip motion of the of this model.